what we're going to be going over here is a nonlinear programming example where we're going to be calculating the production function, and this is similar to the Cobb Douglas production function. Okay, so this is our production function here. So let's just understand that here. Q here, that's the total production or the value being produced. And in this case, we're going to be, Q is going to be profit here that we are generating based on a product that we're manufacturing here. So Q here, our output here is really our profits. And that is equal to Y here, which is our total factor of productivity, or the value here. That's going to be the value or the revenue that we receive here on 1 unit that we're producing of this product. And you take that Y factor here times M times L times K. So M is going to represent our material value or input, and really M is going to be a unit quantity that we're going to be looking at. And then okay, so we have our material here in a unit quantity, and then you take that times the labor here, and the labor is the value here. It's just going to be a unit quantity of labor that we're going to be generating or using here, and then we take it times capital. Well, remember, capital is fixed in the short run, so we're just going to leave it out of our example here. But then you notice here for the material and the labor here, they're raised to exponential amounts here, A and B. You also have C here for the capital, but we're not going to be concerned with that. So really what these exponential amounts, really they have to approximate close to 1 or 100% here. But the A and the B here, let's understand that. A and B, that's the share of the productive output here. So that's what you're looking. They're raised to exponential amounts of labor or material and labor here, but that's really their share of the output here, just get a basic understanding of that. Okay, so let's go and let's really we have to solve for our exponential factors here for material and labor, and let's go and look at that. Okay, again, remember Q, M, and L on a unit basis, we know what those are, and we're going to have to calculate their exponential amounts here for the material and labor. But in our production function here, we're going to expand it here to calculate that profit that we're looking at. Okay, so this is our production function is going to be a profit equals our revenue minus our cost. And our revenue here on a per unit basis, remember that Y value we're looking at, we're going to say we sell this product for $1,400. And then times the material quantity of material that we're going to use raised to the exponential amount times the quantity of labor we're going to raise to an exponential amount here. That's what we're going to be solving for. And the revenue minus cost. The cost here in our case, the material we're using on a per unit basis for producing one product here is $350. And then labor here to produce one product is $200 here. So those are our costs here in our production function our product function that we're looking at. Okay, so that's what we're dealing with. But we have to get this down into some equivalent quantities here between the quantities of Q or the quantity of M and L here that are producing a certain quantity of Q here. And to do that, we got to we'll just drop off our cost function, our cost factor here. We have to get rid of those here, so that's not going to come into our calculation right quite yet. And then this revenue here, this $1,400, we have to bring that into a unit basis as well here. But what you have to do here, when you're, regardless of what your function is here, you have to convert these exponential factors here, this production function, into a linear basis, and you use the log linear equivalent. So let's just look at that. So this is really the key of the whole thing here. We could have jumped right into this in the beginning here, but just to get a good understanding. So what you do is you take the let's just step through this. You take the ln, or the natural log of Q here, and that's going to equal the natural log of 1400 here. This is really just logarithms and how you would handle logarithms, but just basically to get understanding. So you take the log of 1400 here, plus you take whatever exponential amount you here times your material. So in this case, you would have A here times the log here of the material that you're using here. And then B, same thing. B becomes, you just move that here in front of your, as a factor here in front of your, in this case, the natural log here of the ln of labor here. So that's just the rules here on log logarithm rules here. So you have here Q, natural log of Q equals the natural log here of 1400. Add to it A, your exponential amount, times the natural log of the material here, plus B times the natural log here of the labor quantity. Okay, so like I said, we knew what these quantities of Q, A, or M, and L are here, but I'm just looking at it in terms of dollars here. Say my Q here, I knew that an output here of 60 units here of what would that be, of material, plus 120 units here of labor here, gave me $51,272 here as an output Q here. That's not profit, because I left the material and the labor out of the equation here, but just putting that in here, I knew what that was. And then I have the 1400 here in revenue per unit here. And I also just put it in here. I didn't do it. I'm just saying this is what we're going to have to calculate. The exponents here for the material and the labor here. And I've already know what those are, but we're going to go through and calculate that. So what you have to do is you have to bring this into a unit basis, and I'll show you what we're talking about. So the 1400 here, let's just take that and move it over to this side of the equation, divide it into our Q here. This is not the natural log. These are just rough, or just the basic quantities here in dollars. We haven't taken the natural log here. So you get that, and that's going to give us 36.6 here. And that's really the unit basis that we're looking at. So we've brought this Q here into our unit basis to compare it with the units that we have here in material and labor here. Okay, so 36.6 Q is produced by 60 units of material and 120 units here of labor. So we've taken this and we've put it into a unit basis here, unit 1. So we have to do that in our equation here. Okay, so now if we went in and you can do it the other way here. We could have, that's just one way of handling it, or you could just take the natural log here of our output that we had here of $51,272 equals the natural log of the revenue on a per unit basis of 1400 plus whatever the factors are here for A and B times the natural log here of the material and L here. But just to break that down here. So what I would do in this case, I took the natural log here of 51,272, that gives me 10.84. And I took the natural log of 1400, 7.24, so just move that over to the other side of the equation. And my net amount here is going to be 3.60 here. Okay, so that's netting out our logarithms just by moving the natural log here of 1400 over to this side of the equation. And then with the natural logs here, the 3.60, you see that you just raise it to e to the 3.60. That's how logs work here. And that's going to give you a unit basis of 36.6 here, which compares to what we did here before taking the logarithms, just the unit basis here, 36.6. Okay, so we could have just jumped right into this, and I've got all the figures here for the 36 based on the units of material and labor here, but at least this gives you somewhat of an understanding on how you would manipulate these different, in this case, this more expanded equation, this production equation here, to bring it into a unit basis and just see how you manipulate everything around and how it works. But the key is here is this, you take this exponential amounts, just take and make them linear, take the log of the Q here equals the log of whatever y factor you have here. You're going to, in this production function, you're going to have some y factor. In this case, it's 1400. And then you add to it, just multiply, just bring your exponential quantity times the natural log of the m here, and then the same for the b here. Just take your natural log of, bring that down here times the natural log here of labor. So this here, we could have jumped right into it, and we would have known our q and our m and our l here, but we went through all this mechanics here just to see how they operated. Okay, and you have to do that. You just can't go in and take different quantities here. You have to make sure they're on a unit basis between your output here and your inputs when you're trying to calculate your exponential factors here for both of these material and labor inputs. Okay, so now let's go and let's really solve for this a and these b exponents. Okay, so this is the whole thing here, real simple here. I'm using Excel here, data analysis, regression, and what you're doing here, here's my inputs I have here. Q here is my dependent variable. I have 16 observations here. M and L on a unit basis here. I have, those are my, Q here was my output, excuse me if I had said inputs. M and L here are outputs on a unit basis here. And this is what we're going to do. This function here, we're going to fit this data so we can determine A and B here. And what we do is we use a statistical regression here and understand Q is our dependent variable, M and L is our independent, material and labor is our independent variable. We have our equivalent units here, and I'm just showing them here. In this case, that one that we calculated here, 36.6 or 37 here, based on inputs here, 60 of material, 120 of labor, just to understand how that went. We went through a lot of mechanics to get to this point. Could have jumped right into it here, but then we wouldn't understand some of the ramifications here when we looked at production function and how we got to the point that we did. So all you do here is you got your input, or you got your unit values here. You just take the natural log here of each one of those. Natural log here of all those values for Q. Going to be these quantities here. You can see them here. Then you take the natural log here of M. You get all these quantities. Natural log here of L for these quantities. And this is easy to do. Just put into, and I'm using Excel here because it's pretty easy to work with. Just put equals ln and then put your range here from A1 to A16. And the same for E and F here. But the key is you have to, when you're using this regression analysis, just go down here, put this ln Q is going to be your Y range, and then your ln M and ln L here, that's your X range when you put it into your regression, if you're using Excel here. But nonetheless, you have to have some way of taking and regressing, doing a statistical regression for your natural logs here, Q, M, and L. Okay, so let's go down and let's look at our results here. So I run this through Excel, and just breaking it down here. Here is my regression and our coefficients. If you look on your Excel reports, and you're going to get these, you're going to have, in this case, we got that intercept, and that really represents that revenue or that Y value. So if you're ever doing these, wherever you're looking at, I don't care, I'm using it in this example, the intercept here in Excel represents your Y, or that some quantity, quantity here, the fixed quantity of whatever it is here. And then, in this case, it's revenue in this case. And then your M and L here, those are going to be the exponents here. The coefficients, if you look at it, you're going to X variable 1 here, that represents M here, and that's 0.503. We'll look at that. X variable 2 is our L, and that has a coefficient here, 3.115 here. So really, pretty simple to do. We could have jumped right into and done it, so just you understand it. So let's see how what these coefficients, how they fit in. Very easy here. So you have your Q here, and then this intercept the revenue here. Well, that's really going to be 1,400, but the reason I brought it into Unity, you can look at it here. If you raise, you go in and look at it here, E raised to this intercept revenue 0.03, that equals 1 here. So that's just making that, just so you understand, I had to come in and I had to, in order to get these proper variable coefficients here, I had to take this 1,400 and I had to make it a unit of 1, or equivalent unit here of 1 here, and I did that here. And it's shown here in the regression analysis. Okay, so just, we could have jumped right into it here, but just take your, so okay, this would be your coefficient, whatever your intercept is, that's your coefficient here in your production function, and then A and B are those, for M and L are your intercepts here. So just putting them right into your equation here. M, you see that, 0.5035 here. That becomes your exponent, 0.5035 here. Variable M. Real cool here. And then for L here, that's your exponent here, L. So you can see it. See the exponent? So we could have jumped right into it, spent about a couple minutes running through the regression analysis here, but we went through a whole lot of other stuff. And then just to understand here, so we got it. This is our production function equation here. We've got, well, we had to solve for our exponents here. We know what our M's and L's and Q's are, and we know what our revenue on a unit basis is, but we had to solve for our exponents here, and we did it by using the regression, by taking, and we had to convert our Q's, M's, and L's into natural logs only because then we can look at it in a linear form rather than an exponential form. But then we took the linear form, we went in and we did our regression, and we determined our exponents. Real simple here. Okay, and then one last thing here before we move on. Our regression statistic, you want to try there's all kinds of, there's a t-test and so forth, but just understanding the r-squared here, 0.89, and that's telling us that 89%, 0.89, that's 89% of the variation is explained by the variation in Q, which is really a good fit here. If you can get up closer to 100%, the better, and really 100% is not, if you get something like that, you really have to be suspect, but 89% is good, so very good here. So this is our production function. We got our exponent. We know what our exponents are. So now we can go and solve here, and we're going to solve for maximizing our profit in this equation. Okay, now we've got our production function here. We determine what our exponents are based on that regression analysis that we did against the natural log here of Q, M, material, and L, our labor. Okay, so let's fit it into our linear equation, or really it's a nonlinear objective function here, and what we're going to do here is we want to maximize the profit Q here that's measured, and it's some combination of M and L here, and that's what our linear program is going to solve for. All right, so let's just go over this objective function here, see what we're talking about. So first off, this $1,400 here, that's going to be a revenue on a per unit basis for the product we're selling here, and that's really the measure of the output. It's called a units parameter here. So we've got a revenue on a per unit basis here in dollars, so that's what our profit has to come out in terms of dollars here. So again, remember the units parameter, the measure of our output, and you take that times whatever quantity of material you're going to have here, raised to the exponent of that exponent of 5.035. That's what we calculated based on our data that we have here, and then you take that times L here, the amount of labor, raised to its exponent here, 3215. So those come off our regression here. Right off our regression. And then you're going to subtract on a per unit basis the cost of material and labor. And for the product here, that one product, it has a material unit cost of $350, so times that times whatever material quantity we use here, quantity of material, and then you subtract that, and then you subtract out the labor here is a cost per unit is $200 times whatever quantity of labor we used here, we subtract that here from our revenue. Okay, and then the other thing, we're going to have just two constraints just to go through them really fast here. We only have $40,000 available in funds, so you just take whatever quantity of material here times its unit cost on a per unit basis plus the labor here, its unit cost on a per unit basis. Add it together here, that has to be less than or equal to our funds here available, 40,000. And then we also have dollars here. And then we also have one other constraint here, adequate labor here for production. We're just saying that we're going to need a material here has to be less than or equal to 3 units of labor here. So that equates to M here, 1 unit of material minus 3 times whatever unit of labor we have here, whatever quantities we have of labor here, less than or equal to 0. Okay, so now we can solve our, go in and do our linear regression here and solve it. Okay, so moving over here, first for our constraints, I've got those plotted out. That is that $40,000 funding constraint here, 350M plus 200 in labor here. And then we also got our labor here on our vertical axis, material here on our horizontal axis here. And then we also have that constraint here, M minus 3L is less than or equal to 0. Okay, so this is our feasible area shown in green here. All right, so now we can go over and look at, we're going to overlay that production function that we're looking at, that 1400, our production function here with those exponents we're talking about, and subtracting out our material and labor costs here from our revenue here. And by putting that in here, this is where you get those equal product curves, or those isoquant lines, these curved lines here. And I had the computer put in probably 10 different lines here. But these lines, it's pretty hard to tell exactly what they are here, but they really represent this function that we're looking at, this 1400M and raised to the 1400 m, and labor raised to their exponents, plus we're subtracting out those materials. So you're going to get some curvature, or those product lines are because you got that exponential amount, and really represents only 82% of the total revenue here, that we're, our total profit we're looking at here. Okay, so we've got put these isoquant lines in, gives us somewhat of an idea what we're looking at here, and then we've done the max, or the maximum profit here that we're looking at. I looked at constraints versus no constraints. So with the constraints, they come up against, it makes sense here, it comes up against your constraint here for your funding constraint here, and it's sort of in the middle here of this isoquant line. So it means that we're looking at some portion here where this is your profit in this area here, and that maximum profit here based on the constraints here, I'm showing in red here, that red dot on our funding line here. It's 67 units here in material, 75 units here in labor, and it gives us $8,150 here in profit. So your units in material and labor, you'd have to break those down, but on a unit basis, that's what you're looking at. And then I also run the case here, I pulled off those constraints. This constraint didn't fit in here and got rid of this other constraint. And this again gives you it moves the maximum profit up to some degree here. It's only a few $100s more, but it's showing up here. Okay, so that is our, just looking at it in 2D. Now, let's go down and let's look at it in 3D here. Okay, so what I've done here, I just did a surface plot of that objective function that we're talking about, and I got the max profit, that little red dot here, that was for based with our constraints. The blue dot here is without the constraints, but this curvature here, or this surface plot, is really that profit function that we're looking at here. So this is our value here, 0 here. This is where we make no profit here. So anything below it, if you're looking at it here, you got to kind of project this out in 3D here, would be a loss here. You're not making any profit. And anything above it here, that is where you're making that profit. It only went up to what, $10,000 here maximum profit. But you can see, it gives you an idea what you're talking about when you're looking at your different curves here, how it curves. So up on the top here is where you're making a profit, and we've got that maximum profit here, the red dot here, the red sphere they're showing, and then with no, that's with the constraints we have, and then without the constraints was the blue dot here. Okay, so again, L here was our labor, M here is our material quantities here, and along here was our Q, or our profit, shown here. All right, and then if we just go over here and kind of twist this around here and look at it, just take the perspective here, instead of looking into it, we look at it, we'll see, again, it gives you an idea here of that profit line that you're talking about. It's kind of flat across here. It's not curving up or down, but in this area, and just remember 0 here, you project it as anything below 0 would be a loss in here, anything above is shown here. So we kind of have a flat curve up in here. Again, just remember that was for that function that we're plotting here, our objective function here that we're looking at down here. Again, material, labor, and profit here. Okay, so that's just a view of it. Maybe we'll go on and just see how that data fitted up here based on that what we did here to solve for the exponents that we're looking at. Now let's look at how our data was fitted to our production function here using that regression analysis. So this is the production function that we have solved for with our regression, showing the max profit. That little blue dot up here appears our maximum profit. And this ribbon here, the surface plot along here, is that production function itself that I'm showing here. But underneath it, you see, this is the actual Q being on our vertical axis here, M and L here being on our horizontal axis here. Underneath that surface plot, or the production function that was plotted here, is our actual results that we have here, those red spheres up underneath here. Okay, so what I would like to do here is I just wanted to look and see if I can move that our actual data up and cut into the actual function itself here based on the regression that we did here. Okay, so and then let's just go down here. Maybe we can look at it just from the top view here to get a clearer understanding. So here's our maximum profit, that blue sphere. I'll back it off here so you can see it, that blue sphere. But our actual data is still tucked underneath our surface plot here, which represents that production function itself here. So I wanted to bring those up and see what it would take to cut into that function. And it seems like that would be a reasonable idea here to see what it would look at. Okay, so let's look at our first try here. Okay, so what I've done here, I've taken those exponents here in our production function. I moved material from 5035 down to 0.49, 0.5035. I moved it down. Really, it's only what, 0.01 here. And then same for that was for my material. My labor, I moved from 0.3215 to 31. Again, about 0.01 here. And then you can see what's happened here. Just look at the sensitivity analysis. I moved my optimum point from 67 down to 34 for material, and those are the unit quantities, and then for labor it moved from 75 down to 37. But at the same time, my profit nosedive here went from $8,150 down to $4,838. So you can see just a very small movement here in this exponent here, only a hundredth here or 0.00 here cuts your profit right in half, and also the quantities you're looking at. So what it's done here, if looking at our surface plot, going down here and looking at it again, here's our max profit up here that we're looking at, that blue sphere. Now I got those data points that are actually starting to cut through the profit function here. So they're starting to show through here. So I thought that would be a reasonable thing to do. Bring them up here and get an idea what's going on here. Okay, so that's that. Now if we go down here, we can just look at it again. Just a little different view here. Again, there's our max profit here, that blue dot, and then they're cutting through here. Just remember, we had here, this is 0 here, and below here, and below 0 here was our negative profit, or not making any profit. Anything above was our profit here. Okay, so we've moved up our data points to sort of cut through the plane with this moving those exponents down just a hundredth, only a hundredth. Okay, and then let's just look at one more shot here. Okay, so here's the case where all I did is I moved this, my M material, my exponent, from 5035 down to 0.02 here. So just a very small movement here. And then again, for the labor, I just move it 0.01, 3215 versus 3100, 0.01 here. Okay, so this is what we were sitting with here, 67, 75, 80. Now we're down to 27, 30, 27 units of M, 30 units of L, and we're down to 4,000 here in our profit. So you can see how just a little bit of movement here in our exponents here affects our profit from 8150 down to 4067. And just looking at our plot here again, I wanted to see where those actual data points are coming through. So they're coming through a little bit, just a slightly more than what they were when we made that first attempt or first sensitivity analysis by reducing our exponents for material and labor. But then our profit sitting up here, max profit here shown here. So this surface plot here gives you an idea again what your function really is. It's nice to look at it in those terms. Again, here's our 0 point. Anything above here, that's for Q, our profit here. Anything below is a negative amount here. So you can see it. So we're sitting up here, pretty flat curve here, sitting up here. Max profit here, and then those are the actual data points. And then if we go down here, just one last shot at it, looking at it, just a little different perspective here. Again, you can see our data points, our actual Q, M, and L here, actual points are coming through our surface plot here, coming through them, and there's our actual max profit at this point here. Okay, so this is just a pretty good way of looking at your functions, get a little bit a better idea of what's going on and understanding just how these things, instead of just looking at them in equations and numbers and so forth, it's nice to plot them out and get an idea of what's going on. And in this case, we looked at just a little bit of sensitivity analysis here and just moving our exponents just a slight bit, only 0.01 or however you want to look at that, as a hundredth causes a great deal of movement here in your profit, difference between a profit and a loss really. Okay, so that'll summarize our discussion.